So how are you doing today, Seamus?
Oh, I'm doing great, Aalyia. Thanks. I'm here in the historic Beaverton, Oregon campus of Tektronix.
Very
Been a
cool.
beautiful summer so far and looking forward to our conversation today.
Yeah, me too. Me too. I appreciate you sitting down with me or standing up to talk to me. Yeah. So I know that there was two kind of releases during PCIM, the IsoVu, the new wideband shunts for the IsoVu isolated current probes, and then there's the high voltage differential probe. Um, And I was hoping we could maybe talk about the both of them, but we could start off with the high voltage differential probe and really just start off with the basics here. So, what, let's start off with what is a high voltage differential probe and why do you need them?
Yeah, sure. So, I mean, every voltage measurement is differential, as you know. It's just that typically,
Yeah,
like the reference lead is at earth ground.
yeah,
But so a differential probe allows you to measure with the reference that's not ground. That enables you to do floating measurements.
yeah,
And even if the reference is changing,
yeah,
swinging up and down, so that gets into common mode rejection, which we'll probably talk about later.
yeah,
But
yeah,
yeah, and you need a high voltage differential probe, just means that you can connect this to a very high voltage that if you put it directly into an oscilloscope, it would blow up.
yeah, yeah. Um, and maybe we can, talk about the key specs in the recent release. It's
Hmm.
the THD P0400, right?
Yeah, that's
So
right.
yeah. Um, can we talk about that? You were covering the CMRR, the common mode rejection ratio. I know that that's one of the key specs. So maybe we could talk about that as well as the bandwidth, etc.
Yeah, so Tektronix's previous high voltage differential probes, they have origins in 1996. So
Yeah,
I mean that's the same year as the Nintendo 64 came out, if
yeah,
you're old enough to remember that console.
yes,
So yeah,
definitely.
like most Tektronix probes, they were way ahead of their time
Yeah,
at the time. So we
yeah,
got a really great run out of them. I mean, we've sold thousands and thousands of those probes.
yeah,
But it was time to refresh this model with a new version with modern
yeah,
electronics.
yeah,
So
yeah.
that's how we came out with the new THDP 0400. So it has twice the bandwidth of our previous high voltage differential probe,
Yeah.
and it can also measure a higher voltage. So we can have 400 megahertz of bandwidth, and it can measure 2,000 volts.
Okay, yeah, right. I did see that the common mode rejection ratio. Do you off the top of your head? I know that it's probably hard to remember the specific frequencies. Oh, don't worry, don't
Let me bring
worry.
it up. Yeah, I definitely don't have it memorized.
Oh, not to worry. Um, well, maybe we could talk about, say, like, why do you need that high common mode rejection ratio, the high bandwidth? Why have more selectable? I saw there was far more selectable attenuation. There was four different settings, I think, versus the previous model, you know?
Yeah, so common mode rejection is important when your reference voltage is changing rapidly.
Yeah,
So for example, in a switching power converter, if you connect the reference lead to the actual switch node, that node is switching from 0 volts to the rail voltage,
mm,
potentially hundreds of thousands of times a second.
yeah,
And that noise will make its way into your actual signal. So common mode rejection is the ability to ignore any change in the reference voltage and strictly only see the differential voltage. So the THDP 400, we can get like 70 dB of common mode rejection, which is pretty good. So it's over 3 decades reduction. So
yeah.
if you have a 200-volt swing, you're seeing less than a volt of swing in your actual measurement.
So,
Um,
yeah, well, please
yeah,
carry on. No, no, sorry to
yeah, and
interrupt.
you also asked about it has more attenuation settings.
Yeah,
Yeah, that's another improvement to basically the noise floor. So the
okay.
more specialized you can pick your range, the
Yeah.
lower the noise you can get. You don't have to compromise between voltage measuring and low noise floor.
Gotcha. Um, so, you know, we could talk, maybe we could talk about, you know, a real measurement scenario where
Mm.
these specs, you know, make a difference. You know, I saw that in the data sheet, it was targeting floating differential measurements. Makes sense, right? Including wide bandgap semiconductor validation and characterization. Maybe we could talk about that a little bit more.
Yeah, wide bandgap semiconductors have really, come to the forefront in the last 5, 10 years. They've reached a point of maturity when they're becoming completely mainstream. And the
Yeah.
biggest advantage of wide bandgap semiconductors is they can switch much, much faster than silicon or IGBT designs. And that gets the switching losses down. And you can also make filter components smaller. So it's all benefits, but what it does is it makes it harder to measure unless you have more bandwidth. So
Yeah.
that's why our measurement solutions have been going higher bandwidth, even for power electronics, which is typically a lower bandwidth application.
Yeah.
So
Yeah.
for example, a wide bandgap semiconductor can switch in like 4.4 nanoseconds. So that's not unreasonable for GaN, and even silicon carbide can switch in
Yeah.
that speed.
Mm.
And with that kind of rise time, you would ideally have about 400 megahertz of bandwidth to measure that.
Yeah, there's that rule of thumb that was based on the first order filter, right?
That's
Was
right.
it 0.35 divided by the rise time, right?
Yes,
Um,
very good. Yes, very good.
um, yes, I saw that and I thought that was quite helpful to establish the bandwidth that you need for your measurement. Um, so was there anything you wanted to add there, that just kind of what a real measurement scenario where the specs make a difference, the
Yeah,
specs with the
sure.
no,
So
yeah,
the high voltage differential probes, a lot of times in switching converters, you'll use them to measure the drain to source voltage of a FET, one of your switching FETs. And if you can measure the drain to source voltage and you can measure the current through the FET, that's how you get power and that's how you get losses. So you can measure the losses very accurately if you can see both the drain to source voltage and the current through the FET at the same time.
mm. uh, so um, do you? I had no further questions there,
Mm,
because we're going to talk about the, you know, the current probes as well, and I think that it all kind of is this ecosystem that helps you
mm.
do these you know, measurements for wide bandgap semiconductors and
Yeah,
etc.
the last thing
Yeah,
I'll say about the THDP is
yeah,
it's powered and communicates with the oscilloscope through our TekVPI
yeah.
connector.
That was the question that I was going to ask. You know, how does that help an engineer versus using another vendor's probe with the Tektronix
Mhm.
oscilloscope? Yeah,
Yeah, so TekVPI provides power and critically communication with the oscilloscope. And that's really handy so we can build user experience features and software features into the probe. So for example, this THCP has 4 selectable input ranges, 4 different attenuations, and we have logic on the oscilloscope that maps perfectly the vertical scale, so you can zoom in or out, and it'll automatically pick the best range in the probe to maximize the dynamic range and minimize the noise.
mm,
So that's an example of something that we can do because we're able to communicate with the probes and because the scope knows the state of its, measurement settings.
yeah.
It can set up the probes to ideally measure.
Yeah, and otherwise you'd be manually adjusting the scales.
Yeah, and you'd
Yeah.
have to remember to do that.
Mhm.
And also, when you go back later, when you document your measurement results, if someone asks you, hey, what range was the probe in? If you neglected to write that down, I mean, there's no information in this oscilloscope that tells you that.
Mm.
Versus if you have a TekVPI probe, you save a session file on the scope, all the probe settings are saved with that. So it's much easier to reproduce setups later, or if you're working with a lab, your local lab in Germany or your lab in Shanghai. I mean,
Yeah.
yeah.
Yeah. So just, a bit more seamless. Yeah. So was there anything you wanted to add with the high voltage probes? Anything that I might have missed? Because I was going to shift to the isolated current probes.
No, that really captures it. The THDP 400 is kind of a no-brainer upgrade. If you're already using the THDP 0200, our previous one, there's no downside to upgrading to this new model. There's only upsides. All the accessories work the same, and the communication with the oscilloscope works the same. So
Yeah.
it's a no-brainer upgrade.
Yeah. So we could talk about the isolated current probes. I know that there's the new wideband gap shunts for the IsoVu probes, but I think the probes themselves are also quite new because they were released in 2024, right? Originally.
Yeah.
So let's start off with the current probes. When do you need to use an isolated current probe?
Yeah, we started development of the isolated current shunt probe. Really, it was through our work with wide bandgap semiconductors, starting with our first optically isolated voltage probe back in 2018.
Yeah.
So we launched the industry's first optically isolated voltage probe in 2018. And it was really to solve the measurement problems of these wide bandgap semiconductors, which at that time were, just basically coming into being presented at APEC and PCIM, and these semiconductor companies were trying to make them mainstream. I think they're fully mainstream now, but back then we were ahead of the time. So those voltage probes are great for measuring voltages all around the switching converters, but it's not long you start doing these measurements when the customers start asking about current. And current measurements are uniquely difficult simply because the typical way you measure clamp is through like a field effect probe. So it's something that measures the electromagnetic fields from the electrons, flying through the system. So that requires like clamping onto a cable that exists or looping around the leg of a transistor package that has to exist. But with wide bandgap, everything's moving smaller and faster and surface mount. So there is no cable to loop around. There is no leg of a discrete package to loop your Rogowski probe around. So what people are moving to is like surface mount and other shunts.
Okay.
So yeah,
that is very helpful. So that was the motivation behind moving to an isolated current shunt probe in particular. There was something else that was, I thought, kind of interesting about these probes. According to Tektronix, they're the first current shunt probes to use RF isolation. And maybe you could talk about this in more detail. What do you mean by RF isolation? What's the benefits of it? And how does the RF modulator and demodulator play into this?
Yeah, that's a good question. So we got the idea kind of back in 2019 of making an isolated probe through RF modulation, which works very, very similar to like FM radio. Like you mentioned, the modulator and demodulator. So there's a high frequency carrier signal, and the customer's input signal actually modulates that carrier and transmits it over an air gap, over an isolation barrier. And then that modulation is recovered on the scope side and then digitized in the oscilloscope. So we had the idea in 2019 to actually have about 12 patents associated with this isolated current shunt probe. And RF isolation is a big portion of those patents.
What's typically used for an isolated current probe? versus, you know, RF isolation?
So when we created the isolated probe
Yeah.
market by creating
Yeah.
our first, we used lasers, we used optics. So
Okay. Okay.
completely optical fibers. So there was absolutely no electrical connection between
Mm.
the probe and back to the oscilloscope. The entire probe head was powered with the high power over fiber laser,
Okay.
and the signal, the device's signal is modulated and then sent back to the oscilloscope where again, it's the modulations are
Demodulated.
covered.
Yeah.
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 And
Yeah.
even communication, because there's microprocessors on both sides, even communication was done over fibers. So it's completely optically isolated.
What inspired, if you don't mind me asking, what inspired the shift to RF from optical, you know, to RF for the current probes, the isolated current probes?
Yeah, we saw an opportunity to make like lower noise
Mm.
measurements with the RF isolation. And it was also a little bit simpler to use our RF expertise versus relying on like optical technologies, which are
Yeah.
mostly optical technologies are designed for like datacom um, industries, so like
Mhm.
fiber optic communication.
Yeah.
And they're really not designed to be in like in a temperature chamber or in a like a vibrating, power electronics environment, or like on a shaker
Yeah.
table of a big like electric
Yeah.
vehicle. So
Yeah. Gotcha.
laser manufacturers, you come to them with this request about, hey, we want to make this laser work at 200 degrees Celsius, and they just go like, what? Yeah.
Okay, that makes a lot of sense. That makes a lot of sense. Okay,
Yeah,
okay.
and we
Thank
we
you.
can't make
Yeah,
the
yeah,
lasers, but we can make a lot of these other
yeah,
ASICs. So,
yeah. And then there is the RF expertise, right? So,
oh yeah.
so let's talk about the shunt-based current sensing. Unless you had more you wanted to cover about the RF isolation. No, okay.
I would say that what's the
Yeah,
purpose of isolation? I get
yeah, yeah,
the
yeah, yeah,
Yeah, the purpose of isolation is to divorce, the probe's reference voltage from the oscilloscopes.
yeah,
Very similar to the differential probe, like THDP.
yeah,
The whole point is to get that common mode rejection.
yeah.
So isolation is another level above a differential probe where we can get over 100 dBs of common mode rejection versus like 70 with a
Okay,
differential probe.
I see. And is that at DC? Uh, or
Oh, it's higher at DC,
yeah,
and
okay.
yeah, so we
Gotcha.
have over 100 dBs of common
Yeah.
mode rejection, even as high as like 1 megahertz.
Mm. Okay. Oh, wow. Um, and that is specified up to how many megahertz? Is it 250 megahertz? Because it's
Yeah, with our
okay.
wideband shunts, they go to
Yeah.
250 megahertz, so that's
Yeah.
where we stopped.
Yeah. I was gonna ask about that, but I sort of wanted to start with kind of the
Mhm.
basics. You know, it's a shunt base, as you're talking about surface mount
Yeah,
current sensing, you know, and that's different from the clamp on current probe or the current transformer. You know, how does it diverge from those traditional methods? Can you talk about that a little bit more? What was used
yeah.
previously and why the shift over
hmm
to shunt-based current sensing?
Yeah, the biggest reason why people are moving to shunt-based current measurements is one is for bandwidth, and two is to lower the inductance of the current loop.
Mm.
So the faster you're switching the current, the more the inductance starts to matter. So if you know the voltage across an inductor equals the inductance times di dt.
Mm-hmm.
So these new wideband gap devices can achieve much higher di dt values. And that makes the inductance of the current loop absolutely critical because inducing a voltage in your current loop can start to blow up devices and lower reliability. Even if they don't outright die, it can lower reliability.
Yeah, yeah. Um, so the shunts, they come in 4 resistance values, so,
Mm.
from 5 milliohms to 5 ohms, I believe. How does an engineer choose the right one for their application?
Yeah, the first step is to see what kind of current you're trying to measure, and you have to pick a resistor that will survive that current. So that's the absolute first step is,
Yeah, yeah,
will this shunt explode or not? So to accomplish
yeah,
that, the first
yeah.
step is our like pulse current curves.
Mm-hmm. Okay.
So depending on how wide your pulse is, whether you're doing like a DC current or like in double pulse test, if you're just
Yeah.
doing a ramp, you can
Mm,
achieve much, much higher currents in a ramp than if you were doing like a DC current measurement.
I see. I see.
So that's the first step is you have to pick a shunt that will survive. And after that, then you can start trying to optimize to get the most bandwidth or to have the lowest insertion inductance.
mm.
So there's a lot of different shunt designs that have different inductance values, and which will basically directly correlate with to how much bandwidth you get out of that
Is there sort
shunt.
of a shorthand equation for this? That
Yeah,
yeah.
yeah, you
Yeah.
could model a shunt resistor
Mm,
just by itself is like
mm.
a series R in series with a inductor L.
Okay.
So that
Okay.
L is going to be the insertion inductance, and then
Mm.
the R is the resistance of the shunt. So that's
And
basically a
mm,
single pole RL, like high
filter.
pass
Yeah.
filter.
Yeah.
And the corner frequency of that is R over 2 pi L.
Okay.
So the
Okay.
lower you want the inductance as low as possible
Mm.
and the resistance as high as possible, and that gives you the most bandwidth. But
Uh,
as we did, there's tricks to get more bandwidth than the resistor will give you by itself, which we implemented in our wideband shunts.
yeah, that's I did want to ask you about that. You know, you were talking about that the inductance being sort of a key
Mm,
spec, right? It's a known challenge for shunt accuracy, even though it's better than the
yeah.
traditional alternatives at high frequencies in particular. How do you engineer the sort of the TICS, right? The wide
Yeah,
bandgap
wideband
shunts.
shunts.
Yeah, yeah, wideband shunts, sorry. To push beyond, no, sorry, to push to 250 megahertz, How'd you do, what were the tricks as you were saying earlier?
Yeah, so since you have that inductor causing a
Mm,
zero in the frequency response, you
mm,
actually want to match that with a pole, like an RC or an
mm,
LC, a
mhm.
pole. So if you add
Yeah,
a low pass
yeah.
filter that with the same corner frequency as, the high pass LR, you can extend the useful bandwidth out further. So the
Okay.
lower the resistance, the harder this becomes. Like I mentioned, the bandwidth of the shunt itself is directly correlated with the shunt resistance. So for the
Yes.
5 milliohm, it was very fine tuning of this compensation circuit.
Mm,
And there's actually 2 layers of compensation circuits in the shunt itself in order
mm.
to achieve 250 megahertz of bandwidth.
That's interesting. Is that the
Mm.
difference between, because you had a video, right? It was a very good video, the Tektronix video on, it was a double pulse test, and it used the isolated voltage probe,
Hmm.
there was the high voltage differential probe, isolated current shunts probe, and the AC/DC current clamps. But in that video, you used a coaxial shunt
Yeah.
alongside the TICP. So that's obviously different than what we have now with the new wideband current shunts. Is that the difference, the compensation, the 2 layers of the compensation circuit? Like, what's the difference between those two?
Yeah, absolutely.
Yeah,
So those coaxial shunts, you'll see them everywhere in power
yeah,
electronics labs. They were really
yeah.
kind of the first on the market and
Hmm.
everyone recognizes them. So I'm always glad to use them in a video or show them at trade shows.
Yeah.
But they have some pretty big compromises.
Mm,
And the number one compromise is that inductance is completely uncompensated on that
yeah.
shunt. So if you connect that to a
Mm,
VNA and look at its frequency response, it starts flat and it just goes up. So
Okay.
all the high frequency, all the ringing is completely exaggerated with those shunts. And so you might go chasing a ghost that doesn't exist. It's just a figment of this coaxial shunts, uncompensated
Yeah.
parasitic inductance.
About how high do they go, usually? Because yeah.
Yeah, I see bandwidth in the, tens of megahertz of useful flat bandwidth. And from there, by 200, by 300 megahertz, they're already in
Yeah.
inductive land.
Okay. Okay. All right. That is helpful to know. Another thing with the shunts is that they have integrated fuses and spark gaps for
Yeah.
protection. Can you talk about a real world scenario where that would save a piece of equipment?
Yeah, definitely. So in double pulse test, it's not unusual for things to go boom
Hmm.
and FETs to give up. And what we find is that a FET will typically fail into a short circuit. So it'll fail closed. So that's kind of a runaway situation where you have the rail connected to ground through an inductor and through just whatever resistance is in that path.
Mm.
And when you have your shunt in the current loop, so now the shunt becomes the limiting factor, and you very quickly get into hundreds of amps, up to 1,000 amp or higher, and something has to give. So what gives in
Yeah.
this point is the shunt will typically fail open, we
Mhm.
found. So
Okay.
now I could draw it if that would help.
Yeah, yeah, yeah.
Okay.
If it's not too much, I know it's a. So yeah, there we go. I can see it. Yeah.
Okay. So here's your, let's say you have 400-volt rail.
Hmm.
You have, here's like your typical,
Half bridge.
these are your half bridge
Yeah.
FETs. So if you're measuring the current of this lower FET, let's say you have your shunt here
Hmm.
to ground, and then I'll draw the inductor.
Hmm.
So when this FET fails into a short circuit, now you have 400 volts through an inductor through to your resistor.
I see.
So you have hundreds of amps,
Yeah, I
and
see.
this resistor is going to blow.
Yeah, that's a lot
So,
easier to visualize, by the way. Thank you for that.
yeah. So when that fails open,
Yeah,
now you have, so the resistor fails open, and here, what do you have connected here? You have our probe.
uh-oh. Yeah.
So now you have 400 volts here, you have 0 volts here, and that's across a probe with a 1 volt like rating. So that's going to explode. If you did not have a TICP, so a lot of people, they put the shunt in the low side, and then they connect this directly to an oscilloscope. So you have a
Okay.
cable going directly from the
Yeah.
cable
So
into the oscilloscope.
that
So
can
now
kill the
you're,
equipment too.
yeah, now you're putting
Yeah.
400 volts directly into the oscilloscope. That's going to blow something up. So
Okay.
what
That
the
makes
what the
sense.
fuse does is that the fuse protects the isolated current probe. The isolated current probe protects the scope. So the fuse sacrifices itself to protect your, $100,000 in test equipment.
Yeah. Yeah. And the probe.
Yeah, and the probe itself.
Um, well, thank you. That is incredibly helpful. Is this a standard thing, even say in the coaxial shunts that you see? Do you see spark gaps in there for
No,
as
there is
well?
no
Yeah, it's
fuses
not.
in that
So you
device.
just have to
No.
be careful. Okay, gotcha.
Yeah.
Okay. Um, well, maybe we can actually, it's helpful that you have it's very helpful that you have a way to show things, because I wanted to maybe talk about, how the high voltage differential probe and the isolated current shunt probes, how do they fit in a sort of a complete power electronics setup? When do you need both? Do you have like a kind of an idea of like a complete measurement setup for maybe a SiC or GaN converter, or where you use everything?
Yeah, sure.
What's the vision here?
So what's extremely common is double pulse tests to measure switching losses. So again, I'm going to draw our same half bridge. And what's really common to do is called a low side double pulse test.
Yeah.
So that's where you're switching this FET on and off, and you want to measure the losses at different operating current levels. So in order to measure losses, you need power. Power, it's current times voltage.
Yeah.
So the voltage you would do, you could do like a plus minus. This is VDS, drain to source voltage.
Yeah. Yeah.
And then in order to get current, there's lots of different ways, but a good way is to put a shunt in series with it. So now the voltage across this shunt, the shunt, that's directly related to the current.
Yeah.
Through this FET. So that equals IS times R shunt. So you switch this FET on and off, the current ramps up, and then you get to measure the current ramps. You turn it off, you wait some time, you turn it back on, and then this second pulse is shorter. So you're interested in the behavior here and the behavior here. So these are your switching losses, PSW. So it's very common you ramp this current up to some operating current that you're interested in, say like 80 amps, and then you switch this FET off, switch it back on, and then you can see turn off energy and turn on energy. You can also see a lot of variables that are important to you, like what's the peak voltage that the drain sees, what's the peak voltage that the gate sees, and those are critical for reliability.
And you'd need the high voltage differential probe for that, or would you need the isolated voltage probe actually?
Yeah, so the TICP is here. This is the isolated current shunt probe, and then this would be THDP 0400. Drain to source. Because the drain to source voltage, it's going to be, in this example, it's going to be 1200 volts max. And it's actually going to be higher because it's going to overshoot.
Right.
So you want a bit above that. And then this will only be a volt or less. So you want that sensitivity and the low noise of the TICP for there.
Thank you. Was there anything else that I might have missed that you wanted to add? This has been immensely helpful. Thank you very much. I do appreciate you drawing it out, because so many times you're having this conversation and it's really hard to visualize.
They can see it in their head, but it doesn't translate.
Yeah, exactly. But was there anything, before I close things out, was there anything that you wanted to add? If you wanted to show visually, then please feel free to stick on the screen, keep the screen going. Otherwise, please,
I'll say another measurement that you'll want to do is you'll want to measure the gate to source.
Yeah.
So this is VGS. And we have a great probe for that. It's called, you can honestly just use a TPP 1000. which is
Are those the isolated voltage probes?
no, this is a
Oh,
really high performance passive probe.
oh, okay. Okay.
But we
Yeah.
can do it with an MMCX connector,
Yeah.
which has really good shielding. So we have
Yeah.
these like MMCX connectors. You probably won't even see that, but
Yeah. Are those are push I forgot the oh my gosh, my brain's not working.
yeah,
Um,
they're used in like RF. They're used in
yeah, exactly.
antennas and stuff.
They're kind of press push kind of
Uh-huh.
connectors. Uh,
Yeah, so
Yeah.
it's coaxial, which means you have a center
Yeah.
conductor and then it's
Yeah.
completely shielded
Yeah.
around it. And they
Yeah.
also click together. So
Yeah.
it's very stable for like a hands-free operation, which this
Yeah.
all
Yeah.
needs to be hands-free because of the danger.
Yes. Right. Right.
And all this is for low side measurements, but of course you have the second FET up here you're also interested in.
Hmm.
So now all your measurements are referenced to this node right here in the middle.
Hmm.
This is the switch node that's switching, back and forth like crazy. So
Yeah.
that's when you need very, very good isolation is up here. So that's why we actually specifically made the TIVP to do high side VGS. So that's the optically isolated voltage probe
Hmm.
for high side VGS.
There we go. Finally, the isolated voltage probe comes in. I've been mentioning it so many
Yeah.
times. But great.
Yeah,
Okay,
that's what it was
great. Now I know.
specifically
Yeah,
designed to solve.
I
Has
see.
amazing common mode rejection and it's completely optically isolated. And it was really critical for a lot of this GAN and SICK research 6, 7, 8 years ago. Now we see the fruits of it because everyone has an optically isolated voltage probe now, and the products, the wide bandgap products, have reached a level of maturity that Infineon is selling them as a complete like solution. It's
Mm.
not an experiment anymore for the PhD lab. It is a real product that you can just buy.
Yeah, yeah. Almost it's standard,
Mhm.
at this point. Yeah, very cool. Um, I don't have any further questions. Anything else that
So the double pulse test has seen a lot of mileage. It's gotten a lot of mileage out of this testing, and
mm,
I'm happy to say that when I first joined Tektronix, the probes team in 2019, we were doing
mm,
double pulse testing then.
yeah,
So
yeah,
I'm really happy that we were so connected with where the industry was going and the tests it was using. Because as a test and measurement company, it's really important that we understand how the customers are actually measuring their devices and able to do the same measurements in our lab. So
yeah,
it's paid off immensely to have invested in that really early on. And
yeah,
I'm excited to see where the industry goes next. I know that
yeah.
we'll be there and we'll be ready.
Yeah, I mean, speaking of which, I mean, since we're, covering that, being up to date, and aligned with where the industry is pointing and, helping customers with real problems, is there anything you sort of see on the roadmap in the future that test and measurement could help with?
Yeah, a big topic at PCIM this year was high voltage GaN.
Hmm.
So this is using gallium nitride, which was
Yeah,
really, it was pitched at like consumer electronics and little, chargers for your MacBook.
yeah,
But it's seeing applications up to 1700 volts. So,
yeah,
GaN might end up being, in electric vehicles and DC fast chargers and
yeah.
end up performing really well. And GaN is tricky because the inductance of that current loop is even more critical because GaN's
Hmm.
even faster
Hmm.
than SiC.
Hmm.
So
Yeah,
I see everyone pushing towards lower and lower inductance current measurements and
yeah.
also higher and higher bandwidth current measurements.
Hmm. And what are some tricks there? I imagine the shunts have to have a wider bandwidth at that point and
Oh
higher current
yeah,
ratings and lower inductance. Yeah.
yeah. This industry has benefited a lot from test and measurement vendors coming in and starting asking very pointed questions. Because, resistor manufacturers, they are like, they sell reels of millions, at a time. They know a lot about their process, but you ask them any questions about AC performance, insertion inductance, how that changes based on how they trim the resistors. It's just crickets. You won't see any spec published on their data sheets about it. So us test and measurement people coming in and asking these questions and having our own ideas how to improve the inductance of a resistor has led to a lot of innovation already. And I know more is going to come out.
Well, I'm very excited to see more come out. This has been a wonderful conversation. Thank you so much for your time, Seamus. This has been great. I've learned a lot, and I do appreciate that. Thank you.
Yeah, thanks, Aalyia.